Welcome back, everyone, to the Brown Track. We have with us Rafał, who is a cloud-native tech lead at Hazelcast, a very fascinating company, and he has a resume to dazzle all of us, all the coolest technology on there. He's going to be talking to us today about mutation testing with PIT, which is something I've genuinely never heard of about before. So I'm very excited for this. We're going to learn how to trust our unit tests. I'm obligated once again to remind you to ask your questions in the Q&A box. And if you do so, you go into the draw for some packet books. Very exciting stuff. So with that, I'll leave it to you, Rafał.
Hello, everyone. Thanks, James, for the introduction. I'm super happy to be here. I'm speaking to you from Krakow, from Poland, and sharing right now. And you should see my slides. So let's start with the mutation testing with Pete. But before that, just a few words about myself. So as I was introduced, I'm a cloud tech lead at Hazelcast, but before I work at Google and CERN, I'm also an author of the book Continuous Delivery with Docker and Jenkins, and from time to time I do trainings and conference speaking, but my daily activity, I'm just an engineer. A few words about Hazelcast. So Hazelcast is a distributed company, it's an open source company. We produce Hazelcast, which is a platform for in-memory data computing, in-memory data store. So everything where the latency matters, you can try Hazelcast. So our talk will start with NASA. So let me tell you a short story about NASA and what happened in 1999. Because in 1999 in NASA, it was an important year because NASA sent a spacecraft, which actually to Mars, and it actually burned in the atmosphere of Mars. And it is somehow related to testing and the mutation testing. And even though mutation testing was discovered in 1971, it was not really used until 2012. And so all the answers will be answered like in this talk. So let's start with the story about NASA. So imagine like two engineers talking to each other. And one engineer said, like, I wrote code for the spacecraft. How do you know that it works? I just know, or I feel it. So that is actually what could happen in NASA. So the code was not tested. So in December 1998, NASA launched a climate orbiter spacecraft into space. And this device weighed almost half a ton, and it was sent to Mars. And going from from Earth to Mars, it takes around half a year. So everything was fine until September 1999, when all of the sudden contact with the orbiter was lost. And now what happened? So there was a bug in the code. The ground computer calculated everything in a non-metric system. However, so they used pounds, and the orbiter calculated everything in metric systems. So they used kilograms. And there was no conversion in between, so the speed of the orbiter was too fast, and the orbiter passed too quickly through the atmosphere of Mars and just burned. So there were no people on board, luckily. So you may say, okay, shit happens, build another one, send it again. But guess what? You know, these devices from NASA, they're super expensive. So this one that you see on the slide, this one costed more than 300 millions of dollars. So if you cannot even imagine this amount of money, so this would be how like 234 Americans work all their lives. In case of Poland, it's even worse. It's more than 700 people from Poland. And that is just because of like some engineers not testing their code. So how this conversation should look like if you imagine like jokes aside, like how this conversation of two engineers should look like. So I wrote code for the spacecraft. How do you know that it works? I wrote unit tests. How do you know that your tests work? Come on, really. So really, I mean, we write code and then write tests to test the code. So then what? Then we should write tests to test the test of the code, and test to test the test of the code, and test to test. It just doesn't matter. Like, so if we cannot say that tests are good, so what is the use of writing the tests? So does testing make sense at all? And actually, yes, there is a method of testing your test without writing more tests. Imagine the following code. So like the simplest code you can imagine. We have a production code that all it does, it sums two numbers. So we write unit tests for them. And how do you check that the tests work? So we run code coverage usually. But what does the code coverage check? So according to common sense or the guru of common sense, which is like Uncle Bob, he says coverage does not prove that you have tested every line. All it proves is that you executed every line. And that is a big difference. Because we could have like perfectly well code coverage for our code without no assertions at all. So we could write the test like this and have 100% coverage, even though it's actually we don't test anything. So we need something better. We need something better than just unit test and code coverage. And this something better was actually found by Richard Limpton in 1971. So this guy, Richard Limpton, he asked a more fundamental question. So he said why do we write tests at all? And he came with the conclusion that we write tests to detect bugs. So think about it for a moment. So if you are sure that there are no bugs in the code, there's no reason to write tests. So your test is as good as it detects bugs in the code. So we could reverse this strategy and start introducing artificial bugs and check if our tests fails on them. That is exactly what Richard Limpton suggested in his paper, in his white paper, which was called Fault Diagnosis of Computer Programs. He mentioned something in this paper, something like this. If you want to know if a test suite has properly checked some code, introduce a bug. So how does it look like in practice? Let's go back to our example. So we had the most simple code you can imagine. How could we introduce a bug to such a code? We could, for example, change plus to minus. That is definitely a bug because we wanted to have a sum of two numbers and we have a subtraction of two numbers. So what we just created is actually what is called a mutation of the production code. Now we can run our test suite against this code, and our test should fail, because if our test does not fail, it means that our test is useless. It does not even detect any bug. We changed plus to minus, and tests are still green. So that something is definitely wrong. And this is the whole idea behind the mutation testing, that we change the code and run the tests. And actually, yes, that's the whole idea of the mutation testing. So all the rest of the talk, I will just make it show you how it works in practice, and maybe first introduce the terminology we will use. So this artificial bug we just created is called a mutation operation. code with the artificial bug is called a mutant. When the test fails on the mutant, it's good because we know that the test is good. We say that that we killed the mutant. However, if all tests survived, if all tests passed, even though we created a mutant, so the test succeed on a mutant, we say that mutant survived, which is bad, which means that our tests are useless. So we mutate the code, we change plus to minus, and if at least one test fails on them, it says we killed the mutant. If all test passes, we say it survived, it's bad. So in this context, killing is good. If we kill all the mutants, our tests are perfectly fine. So the idea is pretty simple, but the first thing you may think about, and it's the first thing I thought about when I first heard about mutation testing, was that, my code is much more complex than just adding two numbers. So I have so many places that could be mutated. How to grasp it all? And for this, we have that is why we have like a lot of different mutation operations. So for example, we have math mutation operations. So we change plus to minus, minus to plus. We have boundaries. So we change greater than to greater or equals or less than equals. So we take all these boundary changes. We change the negation. So some conditions should be equal, but we say it should be not equal, etc. And we have some more complex operations. So remove the if statement, remove method calls, modify return, modify constant, and there are some more operations you can do with the code. So you take your whole code base. This is your whole code base. And you apply all these mutation operations. So you generate a mutant, you actually generate a lot of mutants. So you create a lot of binaries. And you run your test suite against these binaries. And if for each mutant there's at least one test that failed, it's all good. Your tests are good. But if there is any mutant that survived all your test suite, it means that you have a code which is not well covered according to the mutation testing. And that is a problem. Do I need to change the code on my own? Obviously, no, nobody would do it. So for Java, there is a very good tool which is called Pit mutation testing, and we will see how it works in practice right now. That is actually what I use when I program in Java. I test my code with Pit. Let's first see how you can do it, how you can introduce it like in your IDE to check every code you write. You can actually run the mutation testing from your IDE. So let's stick to this example with the calculator, just two numbers and this tests, which does not test anything. And let's see what happens if we run it in IntelliJ. So this leads us to our first demo. So if you'd like to run it, run this demo from IntelliJ, you need to have like a Pit plugin installed, and then you can see, then you can run the. So you see our calculator project. You can see that we have our unit test, which does not actually test anything. We can see it the code cover. We can check even the code coverage, how it looks like. And you see it's like 100% for class, methods, lines. So it all looks good, even though we know that it does not test anything. So how to improve this this coverage checking? So we can to use this Pit, we need to edit the configuration, add a new one. We'll add a new one for the Pit runner, and then in Pit runner we will need to specify the configuration. And to specify everything we would like to, we can give it a name, then the target classes where it should be run on. We can run it on all our classes. Then when the report should be generated, some output format. So let's look what we can check. And that's actually it. So if you click OK and run this, we should see the PIT framework in action. So it generated some mutants, run some tests. So if we look, yes, this is our like what it logged out. So let's maybe look closer. So this is one of the output of the PIT framework. So it said I generated one mutant, which was changing the plus to minus, and it survived. You see, it's not killed, it survived, which means that our test suite is not good enough because the mutant survived this survived all the test suite, which is what we expected actually, because our test suite did not have even one assertion. So how it could test anything? You can see like the outcome of the, it can be also timeout if because you can imagine like if we mutate random things, we can generate some infinite loops. So timeout is not necessarily bad. I mean, timeout is still okay. But worst thing is if it survived the test suite. So this could be an improvement to our test. So we could write a proper test. So like with the proper structure. So given when then and with the assertion. So that will be an improvement of the test. So so this would provide, this should kill the mutant. You may also act like, you know, and then if we run it, you will see that that the mutant was killed. But before we see it in action again, like you may ask, but do I really need to read the console? And obviously not. Nobody would read the console. We need a proper code coverage report, which PIT can provide. And let's see in action right now with the second demo. So if we, this is our updated test. So this one provides like, it should kill the mutant. It provides good coverage, but also good coverage according to PIT. So if we run this PIT again, we will see that it actually killed the mutant. So this is one thing. So good, 100%, 100%. Our test suite is good. But we can also click on the open report in browser and browse the code with code coverage according to the mutation testing. And this is very nice because we can see that that you can check every class, what happens, what mutants were created, what lines were covered or not. In our case, the code was pretty simple, so we can see that that there are actually 2 mutants created, and both of them were killed with our tests. What you can see also at the bottom is what mutators are active, because you can configure PIT to not activate all the mutators. And we will see in a second why you may not want to activate all the mutators. So you see, like you can have like very well, like it's a very well tool actually. If you I actually use it frequently when coding something in my IDE, just to run to check if instead of running code coverage, you only run PIT, and then it gives you better feedback about your test quality and if you covered all the scenarios. But still, like you may ask, like, what about bigger project? Everything works fine if you look at, you know, and at the at such a small project as our calculator example. When you just sum 2 numbers, it's too easy. So I prepared like the third demo and the last demo on the Hazelcast Kubernetes plugin, which is not a very big project. It's 5,000 lines of code, 12 classes, but it's something that is actually, I mean, we use it. It's like a real life use case. It's not something we actually really used mutation testing on this. So it's something that really makes sense. So I will show you how to check. You take like a random. This is open source project, so treat it as a random open source project, how to run mutation testing on this and how to make any analysis about it. So let's look like the third demo for this presentation. So let's look at this. So this is our project, Hazelcast Kubernetes. It's a Maven project, so we can use look at the POM, and we added here the profile for pit testing, where you can specify some parameters. I will not go into details, but you can specify different methods how to run this. But all you need to add actually to your project is to this part, to the Maven, and then we can clone this project. So if you clone this project, we will see in a second. Let's clone it, and then we'll see in a second how to run pit and generate a pit report against it. So go to the project, and now if we use Maven and use this profile pit test where we added the pit dependency and run the mutation coverage, it will run mutation testing against all the code base and generate a report how well our tests cover the code. Obviously, it's not. I can tell you that it's not. So we could look at the report, but actually, what we did, we actually integrated with the GitHub Actions, and this is what I really recommend doing. So the pit is running with every push to master, and it's run exactly the same command. And you can publish this report to the GitHub pages, and then you have like all the time. So you can all the time go to the GitHub pages and see how well your code is covered, which is perfect. So that is what we did. And if you see how this action run, you can go to this action and see that this report that that this pit coverage was run properly, and yeah, you see it's like a lot of things happened here. So it's even as for a small project, but you can it was somehow expected, to mutate every operation. It's a lot of work. And then we can go to this GitHub page where we generated the report and see, that is the report for the whole Hazelcast Kubernetes code base. It's a little weird looking at this because most of the code was actually written by me, so it's not so nice to look at your code. It's always better to run it on your on some other code base. But let's look at this. So you see some parts are not actually well covered. This is just initialization. This is this part definitely could be improved according to the tests, because even if we remove this line, there is the test pass, so that is definitely a place for improvement. So you see there, like it gives you some very interesting. So I really recommend like also doing it for your project, especially if you work on the open source project. Then you can generate this report on GitHub pages and make it even public. Okay, so if that is so great, so let's come back to our question of this talk. So why NASA engineers, they didn't use it in 1998, even though it was discovered in 1971? And there is a reason for this. So Richard Limpton discovered this, or wrote a white paper about mutation testing in 1971. And then there was, for a long time, it was not used. Then at 2000, there was a first Java-based framework introduced, but it was not wildly popular. And then Pit was started in 2012. This first one was called Jester, but it was not very popular. Pit is relatively popular. So you see, like there is this a lot of years in between, like 2012, 1971. It's what happened during this year. So, and why it was not so popular. So there are like two really like there there are two problems with the mutation testing and how to implement them efficiently. One is so-called equivalent mutants. So let's look at this code. So this is like this could be a production code. But now think for a moment. If we mutate the second condition, for example, remove this condition. The semantic of this code, or this code and this code, is exactly the same. I mean, there is it will work exactly the same. And therefore, all the tests will still pass. And that is expected. So equivalent mutants cannot be really killed. And it's hard to tell what operations will cause equivalent mutants. That is why it's somehow problematic to say, like, you get the point that we have some kind of false positive that we think that the code was wrong, but actually it was right. So how did the PIT framework address it? It didn't address it like the whole problem, but the mutators that are highly probable to generate equivalent mutants, they are disabled by default. So you can play it with different mutators, and then you will have mutate, but they are by default at least limited. But there was a second problem with the mutation testing, which was slow performance. And those 4 years like a big problem. Because you can think for a moment, like we generate a lot of mutants, we generate a lot of code, and there are a lot of tests. So even if you look at this picture, like if you run all the combinations of tests and mutants, you will have more than 1,000 on this picture. It's like you will have more than 1,000 combinations. So, and this is like a small picture. In reality, you will have much more mutants and much more tests probably. So the idea that PIT framework introduced was to run first before running any mutation operation. Just you have all the tests and run the standard coverage and see which test touches this code base. And now if the mutant was generated from this code base, run only this test, not all the tests against the mutants, because other tests will not, they anyway didn't touch even the code, so they are kind of useless. And then we don't have like the combinations of all tests against all the mutants, but only some tests against the some mutants. And some other optimization in terms of the performance done by PIT was the tests are run in parallel. There are some test prioritization. So if it is more probable that this mutant will cause some problem, it runs first, etc. So the PIT did really great job in improving the performance and disabling the mutators that may cause equivalent mutants, and that is why it became usable and why it's used in production in the testing pipelines by a lot of companies. So okay, you may say like, okay, I'm convinced, it looks good. I will try it right now. I'll try mutation testing. I will try PIT. Rafał, the talk was great. You can, but I will use it. I'm convinced. But what about my team? They will not run it from IntelliJ, or they will not generate some report. So how to introduce it to the team? And let me tell you a story here. Not so long time ago, I worked in the banking industry. And so you can imagine like important stuff like NASA, big money. And our team was distributed across 3 locations. So one was in USA, Stanford, the second one was in Poland, and the third one was India and Hyderabad. And each team developed some separate modules, so there were not so much interaction in between. And since it was a banking industry, we had a very strong push on having tests and avoiding any bugs. So the bar was very high and we had like a bar of 100% test coverage. And that was the threshold set on our continuous integration server. So you couldn't push to master anything, or you couldn't merge any PR which was not 100% covered. And everything was fine. I was happy developing code, writing tests, and everything was fine until a moment when I had to add a new module. So when I had to add a new module, and the construction of the module was that each module had its own main class, which was to start the module. And the whole problem was that I wrote this module and then I wanted to add tests. And I thought since the bar was on 100% code coverage, how to add tests for the main class. Because if I test the main class, then I effectively run the whole module. So it was not good for unit testing, and it was actually in the system, it was not even possible to do it. So there was something like, which I would call like main class paradox, that it's difficult to test, like unit test your main class. Sometimes it's even impossible because to really test main class, you actually do more integration testing or end-to-end testing, not necessarily unit testing. But I had to strive for this 100% coverage. So I thought, what to do with this? And if you don't know what to do, like just check what others do. So I started to read like the code of the whole project and the other modules. And I read all these modules and I checked their test for the main, and there was given when, but there was given when, but no then for the main class, and for a lot of other classes as well. So then I actually said, come on, what are we doing here? I don't know what to do with people who write tests with our assertions. Like, I don't know, should we laugh on them or get angry, but the main question was how to prevent it from happening. And that is why what we later did, it was to actually add mutation testing into the CI. So no matter if you run Jenkins, Travis, GitHub Actions, whatever CI, you can always integrate with the Pit or some other framework and use it in the pipeline. Use it as a check. I mean, check if you want to have threshold on the code coverage, do it, but according to mutation testing, not the normal code coverage. And actually, by that time, we used Jenkins. We introduced the mutation testing, so it was good. Actually, it improved our code quality. It even detected some bugs, as far as I remember. So yeah, you may still say, okay, it all sounds good. I buy it, everything, but do people really use it? I've never heard about mutation testing. Do people really use it in production? I can tell you, we started using this in this banking industry. We started using this for modules now in Hazelcast, but also some other companies like CERN is well known for using mutation testing. Some Norwegian public voting system, they announced that they used mutation testing for their system. So, and more companies are joining this trend, which is, I would say, it's not longer new. I mean, Pit was created in 2012. It's almost 10 years. But a lot more and more people are adding this to their CI pipeline. So, and that is a good idea. So I really recommend doing this. So test your tests, because it gives you the freedom to refactor test. It gives you trust to your test, and it ensures that tests are effective. And otherwise, if you don't, you may lose. Shit can happen, or you can lose a lot of money, or you may feel shame across the world, or hear laughter, or someone may get angry on you. So better test your tests. And with this last slide, I would like to thank you for listening to this talk. It was a pleasure to speak here.
Great stuff. I actually I'm amazed at how useful that is. I'm going to be installing that probably tomorrow if I can get the chance. We've got about 10 minutes left, so plenty of time to go through questions. I even have a couple myself, honestly. It's quite
Great.
exciting. So we'll go through everyone else's so I don't hog the time. But someone has asked, is mutation testing just for unit testing?
Technically, no, because anything you could run in Java, you can. I mean, you've seen it. I just use JUnit for this, so everything you can run in JUnit, you can use mutation testing for this. The problem is that how much time does your tests run? Because usually, like this end-to-end testing or integration testing, if they, for example, take 10 minutes to run, you need the whole environment, then it would take really enormous time. Like you will need 24 hours or something. Then it becomes less pragmatic. That is why what I see in practice, it's usually used for unit testing or integration testing if they are small in terms of time.
Yeah, got to be fast.
Yeah, they gotta be fast. Yeah.
Istvan has asked, how does the tool handle equivalent mutants? I think you might have covered a little bit of this, but
yes, it does not. It does not. The problem does not disappear, but the good thing is that what Pete did is that there are some different mutators. One mutator is, for example, remove if statement. Another can be remove method calls, etc. So mutator is just what changes your code, and there are different types of mutators. And in Pit, the mutators which are highly probable to generate equivalent mutants, they are disabled by default. You can still enable them, and actually, at some point, if you've seen the one of the demo, at some point there was some which mutators are active. So you can in the report it says which of mutators are active in your run, and you can just enable them. But Bit what they did, they disabled this one which are highly probable to generate equivalent mutants.
Yeah. Someone else has asked a similar question. When our test is summing two zeros, how will the mutant look? The assertion for 0 plus 0 is equal to 0. 0 minus 0 is 0 as well. It's a tough one to mutation test, I guess.
Yeah, this one. This is exactly like this is the same question actually. It's this 0 plus 0 is an equivalent mutant. So no matter what you do, it's the same. So it may happen. But we try to this not to happen, because you will get like basically, I mean, if you really have a code like this and you have like equivalent mutant, your report will be wrong. That's all. I mean, so
yeah, I haven't.
It's not the end of the world, but
yeah. Someone else has asked, how fast does it run on medium to large projects from your experience? Do you typically run it nightly, or do you run it like on every push?
For our plugins, which are, you've seen, they're relatively small. So for this Kubernetes plugin, I didn't show it locally, and that was the reason why I didn't want everyone. I mean, it takes time. So in our GitHub action, I think it took 5 minutes for well-covered actually project with it was 5,000 lines.
Yeah.
So it's quite a lot, I would say, but it's still, for a bigger project, you will need a nightly build. Yeah. But we run it after every push master.
So any monolith would need to do it. Yeah, I don't nightly. Yeah. So do you have experiences in compiled languages such as C++, which I think you do, John?
With mutation, I generally have, but not with mutation testing. So I cannot help here in terms. So yeah.
Just be a lot slower.
Yeah. I can. I mean, I work for like professionally like 1 year with C++. Now I work a lot with Golang.
Is there a Golang plugin for this?
I don't know. I haven't tried with Golang, to be sure. I mean, for Golang, for sure, there is library, because Golang is very like open source, driven. So, but I cannot recommend anything because I haven't tried. Pit is like for Java, and it's very mature, I would say. For other languages, I don't know.
No other languages? All right. Someone else has asked the same question. So unless you know any other, I know Striker is one that I was reading during your talk that I'm going to be implementing definitely over the weekend at least. So when do you recommend using Pit on a project, for regression testing or something else? Was a question.
Yeah, I would start right now to at least know the condition of your project. Even if you don't introduce like a boundary, like a threshold that it will, I don't know, your CI will fail if you don't cover it in 50%. You might not need it, but I would start right now to at least see this report and see, where we it's like how you treat like the technical debt. I mean, you first observe what is the current state, and then think how to act upon this. So that is what I would recommend doing. So first start generate this report, and at least know, at least have this knowledge, and then you can think what to do about it.
Work it off slowly or something. Yeah. Just like adding linting or anything else that you'd add to your build pipeline. So now that everyone else's questions are done, I'm just curious, is there a way, so I'd assume that it doesn't run every single possible iteration of every single mutation, every single test run. So is there some sort of like seed that you supplied to make sure that the mutations are reproducible, or how do you prevent like super inconsistent builds where like I'm pushing and then a mutation isn't picked up?
They're actually consistent. It's not like randomly generated. They're actually consistent. So every time you run it, you will have the same result. You will not have like a flaky test, because that would be really bad actually. If you this is actually the worst thing that you can. So so every time you run it, it's the same. So they try to run all the mutator operations and like optimize upon this, but only run specific tests for the specific
so you pick
mutants.
the test that you want to run.
Yeah. But yes, but you if you have small project, you can always run every test after on every mutators. But at first, I tried to explain it in one slide. So it tries to first run the normal code coverage, bind which tests are related to which mutants, and then try to kill them. But it's deterministic. It's not flaky.
Yeah. I can definitely see how this would be so much more beneficial than code coverage. I've never found that to be a particularly useful metric because of your exact experience.
Well,
and I had literally the same thing. There was the mandate from on top, like we must have 100% code coverage, and you check the test and nothing's actually happening. So
exactly, well, anyway, you see it all over, everywhere, like the same problem.
That's life. It's anti-lazy developer, which I'm all for. So that was great. I really enjoyed it. I've learned heaps from this session. Thank you for your time. This ends the brown track for the day. For everyone else, we'll be back tomorrow, I believe. So thank you very much. Is there anything else you'd like to say?
No, just thank you for listening. It was super nice for me to speak to you, and thanks, James, for moderation.
Yeah, it was great. I'm super happy that I was here for this one, at least. So thank you very much. See ya.
See you. Bye-bye.